Stop thinking of electrons as little balls. I mean it. Right now, in your mind, you probably have this picture, this comfortable, clean picture of an atom that looks like a tiny solar system. You've got a nucleus in the center, dense and heavy, like a sun. And then you've got these electrons, these perfect little spheres whizzing around it in neat circular orbits, like planets going around a star. Maybe they're blue, maybe they're glowing a little. It's a beautiful image. It's clean, it's simple. It's completely wrong. That image, the one they showed you in middle school, the one that's burned into every textbook cover and science poster, that's the Bohr model. And Niels Bohr himself, the man who invented it in 1913, knew it was wrong almost immediately after he published it. It was a stepping stone, a useful lie to get us closer to the truth. But we've known better for 100 years now, and yet somehow that little solar system is still rattling around in your brain. Let me destroy it for you, completely. Because until you let go of that picture, you cannot understand what's actually happening at the smallest scales of reality. Here's the problem. If an electron really were a little ball, a tiny marble with a surface and a definite position, then you should be able to zoom in on it and eventually see that surface, right? You should be able to point at it and say, there, that's the electron. It's right there at exactly this spot in space. But you can't. Every time you try to pin it down, every time you try to measure its position more and more precisely, something bizarre happens. The electron doesn't cooperate. It's not that your equipment isn't good enough, it's that the electron itself refuses to have a precise position. This isn't a technical limitation. This is the Heisenberg uncertainty principle, and it's telling you something fundamental about reality. The more accurately you try to measure where an electron is, the less you know about where it's going, and vice versa. These two properties, position and momentum, they can't both be known at the same time with perfect precision. It's not that the information is hidden from you, it's that the information doesn't exist. The electron doesn't have a precise position and a precise momentum simultaneously. Nature itself is fuzzy at this scale. Think about what that means. If you try to squeeze an electron into a smaller and smaller box, trying to force it to be here and only here, the electron's energy goes haywire. It starts bouncing around more and more violently. It spreads out in momentum space. You try to grab it, and it becomes slippery, evasive, like trying to hold a fistful of smoke. And if you zoom in with more and more powerful microscopes, if you could somehow see smaller and smaller, you'd never find a surface. You'd never hit stuff. There's no hard shell, no skin, no boundary where the electron ends and the rest of the universe begins. It's more like a cloud, a probability cloud, a ghost. And here's where it gets worse. That cloud isn't even a thing you can touch. It's a mathematical description of where the electron might be if you looked. It's a map of possibilities. The electron, before you measure it, is smeared out across space. It's in many places at once, in a very real sense. And only when you perform a measurement, only when you interact with it, does it choose a location. But even that language is misleading. It's not choosing. It's not deciding. There's no little consciousness inside the electron making a choice. It's just that the act of measurement forces the universe to pick one outcome from a range of possibilities. So what is an electron, really? If it's not a little ball, if it doesn't have a definite position, if it's smeared out and ghostly and refuses to be pinned down, what is it? That's the question that haunted physicists for decades. And the answer they found is so strange, so beautiful, and so utterly different from anything in our everyday experience that most people never hear about it, because it requires us to completely abandon the idea of particles as objects. Let me tell you the truth, the real truth, the truth that took us 100 years to figure out. Electrons are not particles. Photons are not particles. Quarks are not particles. There are no particles. Let's start over, from the ground up. Imagine the entire universe. All of space, everywhere, in every direction, stretching out forever, is filled with invisible fluids. Not water, not air, but something more fundamental. Something that exists at every point in space, even in the darkest, emptiest void between galaxies. These aren't ordinary fluids. These are fields. And there's one field for every type of particle we see in nature. There's an electron field. It permeates all of space. Every cubic centimeter of the universe, including the space inside your body, inside the atoms of your skin, inside the nucleus of every atom, it's all filled with the electron field. There's a quark field. Actually, there are 6 quark fields, one for each type of quark. Up quarks, down quarks, strange quarks, charm quarks, bottom quarks, top quarks. Each one has its own field, and all of them are layered on top of each other, filling the same space. There's a photon field. That's the electromagnetic field, and it's responsible for light, for radio waves, for the glow of your phone screen. And there are more. Neutrino fields, gluon fields, Higgs field. They're all there, all the time, stacked on top of each other like invisible oceans, each one vibrating, rippling, humming with energy. Now, here's the key. What we call a particle is just a ripple in one of these fields. An electron isn't a thing. It's a localized vibration in the electron field. A photon isn't a thing. It's a localized vibration in the electromagnetic field. A quark is a vibration in a quark field. Let me give you an analogy. Imagine you're standing on a beach, watching the ocean. The water is calm, flat, stretching out to the horizon. Suddenly, a wave rises up. It has a peak, a crest. It moves toward the shore. It has energy. It has momentum. You can point at it and say, there's a wave. But what is the wave, really? Is it a thing? Is it an object you can pick up and hold? No. The wave is a pattern in the water. It's a disturbance. The water itself isn't traveling toward the shore, only the pattern is. If you put a buoy in the water, it bobs up and down as the wave passes, but it doesn't move forward with the wave. The wave is a shape, a form, a temporary configuration of the water. And here's the beautiful part. When the wave crashes on the beach and dissipates, where does it go? It doesn't go anywhere. It just stops being a wave. The energy spreads out. The pattern dissolves. The water is still there, but the wave is gone. That's what a particle is. A particle is a wave in a field. When you see an electron, you're seeing a localized ripple in the electron field. When that electron gets absorbed, say, by an atom, the ripple disappears. The energy gets transferred somewhere else. The electron field is still there, everywhere, but that particular ripple, that particular electron is gone. And this explains something that's always been mysterious. Why are all electrons identical? If electrons were little balls, little marbles made of some fundamental substance, you'd expect them to be slightly different from each other. Maybe one electron is a tiny bit heavier, or a tiny bit bigger, or has a small scratch on its surface, but they're not. Every electron in the universe has exactly the same mass, exactly the same charge, exactly the same properties. They're utterly indistinguishable. Why? Because they're all ripples in the same field. They're all made of the same underlying stuff. Just like every wave in the ocean is made of water, every electron is made of the electron field. There's only one electron field in the entire universe, and every electron is just a different vibration of that one field. Think about that. When you look at your hand, you see solid matter. You think you're made of trillions of tiny particles, but you're not. You're made of ripples, vibrations, patterns and fields that fill all of space. Your body is a symphony of quantum fields, all vibrating together in an unimaginably complex dance. Now, I know what you're thinking. Okay, fine. Particles are waves in fields, but they still feel like particles, don't they? I mean, when you detect an electron, you get a click on a detector. A single localized event. It doesn't spread out like a wave. How does that work? Great question. And the answer is one of the deepest mysteries of quantum mechanics. When a field vibrates, it can have different amounts of energy. And here's the weird part. The energy in a field is quantized. It comes in discrete chunks. You can't have half an electron. You can't have 1.3 photons. The field can only vibrate in certain specific ways, and those ways correspond to whole numbers of particles. So when the electron field vibrates with the smallest possible amount of energy at a particular location, we say there's one electron there. If it vibrates with twice that energy, there are 2 electrons, and so on. But the field itself is continuous. It's everywhere. The particle-like behavior, the fact that you get a click on a detector, a single localized event emerges from the way the field interacts with other fields. When the electron field interacts with the atoms in your detector, energy gets transferred in a quantized way. A discrete amount of energy, 1 electron's worth, gets absorbed, and that feels like a particle. But deep down, it's all fields, waves, ripples. There are no little balls. All right, so if everything is just fields, vibrating and rippling, How do things interact? How does anything push or pull on anything else? Think about a magnet. You hold a magnet near a piece of iron, and the iron jumps toward it. There's a force. But the magnet and the iron aren't touching. There's empty space between them. How does the magnet reach out and pull the iron? For centuries, this was a profound mystery. Isaac Newton himself was deeply bothered by it. He invented the theory of gravity, which says that every mass in the universe attracts every other mass, but he hated the idea that this force could act across empty space. He called it absurd and said that no one with any competence in philosophy could believe it. But he couldn't figure out how it worked, so he just described the math and left the mechanism as a mystery. The answer, it turns out, is fields. The magnet creates a disturbance in the electromagnetic field. That disturbance spreads out through space. When it reaches the iron, it pushes and pulls on the electrons and nuclei inside the iron atoms. The force isn't traveling through space, it's already there. The electromagnetic field is everywhere, and the magnet is just changing its configuration. But we can go deeper. How exactly does one field talk to another field? Let's zoom in. Let's imagine two electrons sitting near each other. Electrons repel each other, right? Like charges repel. But how does one electron know the other one is there? Here's where it gets wild. The two electrons are both ripples in the electron field, and the electron field is coupled to the electromagnetic field. That means that when the electron field vibrates, it shakes the electromagnetic field. And when the electromagnetic field vibrates, it shakes back on the electron field. Now, imagine one of the electrons jiggles a little bit. That jiggle creates a ripple in the electromagnetic field, a photon. That photon propagates through space, like a wave spreading across a pond. When it reaches the second electron, it gets absorbed. The energy and momentum of the photon get transferred to the second electron, and the second electron recoils. From the outside, it looks like the two electrons pushed each other apart. But what really happened is they threw a photon back and forth. This is how forces work in quantum field theory. Forces are mediated by particles, or rather, by ripples in the fields. The electromagnetic force is mediated by photons. The strong nuclear force, which holds quarks together inside protons and neutrons, is mediated by gluons. The weak nuclear force is mediated by W and Z bosons. And here's where it gets even stranger. These mediating particles, the photons, the gluons, they don't have to be real. They can be what we call virtual particles. Let me explain. In quantum mechanics, energy can fluctuate. For a very short time, the universe can borrow energy from nowhere as long as it pays it back quickly enough. The shorter the time, the more energy you can borrow. This is the Heisenberg uncertainty principle again, but applied to energy and time instead of position and momentum. So when two electrons interact, they can exchange a photon that doesn't have enough energy to exist on its own. It's a virtual photon. It pops into existence, carries the force from one electron to the other, and then disappears. It exists only for the briefest instant, in the space between the two electrons. Virtual particles are everywhere. Right now, all around you, fields are exchanging virtual particles constantly. They're the messengers of forces, the glue that holds matter together. And they're not real in the sense that you can't detect them directly, they're too short-lived, but their effects are very real. Physicists visualize these interactions using something called Feynman diagrams. These are little pictures that show how particles move and interact. You draw a line for each particle, and when two particles interact, you connect their lines with a wavy or curly line representing the force-carrying particle. For example, imagine two electrons approaching each other. You draw two lines, one for each electron, moving through space. Then, at some point, you draw a wavy line connecting them, that's the virtual photon. One electron emits it, and the other absorbs it. The electrons' paths bend away from each other because they've exchanged momentum. It's like two ice skaters throwing a heavy ball back and forth. When one skater throws the ball, she recoils backward. When the other skater catches it, he also recoils backward. From a distance, it looks like they're pushing each other apart, but really they're just exchanging an object. Except in the quantum world, the ball is a ripple in a field, and it doesn't even have to be a real ripple. It can be a virtual one, borrowed from the vacuum for just long enough to get the job done. This is the dance of forces. Fields, vibrating, rippling, exchanging energy and momentum through virtual particles. Nothing is solid. Nothing is static. Everything is in constant, shimmering motion. Now, let's talk about the most terrifying, most beautiful part of all this. Empty space. The vacuum. Nothing. What is nothing? You might think that if you took a box and removed all the atoms, all the air, all the light, every single particle, you'd be left with nothing. Pure, empty space. A void. But you'd be wrong, because the fields are still there. Remember, the fields aren't made of particles. The particles are made of the fields. The electron field, the quark fields, the electromagnetic field, they don't go away when you remove the particles. They're always there, filling every point in space, even in the darkest, coldest, most isolated void you can imagine. And here's the kicker. Those fields are never completely still. Even in the vacuum, even when there are no particles, the fields are fluctuating. They're trembling, vibrating, rippling with tiny, random disturbances. This is because of quantum mechanics. The uncertainty principle says that the energy of a field can't be exactly zero. There's always some minimum amount of jittering, some irreducible background noise. The vacuum is not a calm, flat surface. It's more like the ocean during a storm, with waves rising and falling, appearing and disappearing. These fluctuations are real. They have measurable effects. For example, there's an experiment called the Casimir effect. You take two metal plates and put them very close together in a vacuum. The plates restrict which wavelengths of electromagnetic field fluctuations can exist between them. Only certain waves fit in the gap. But outside the plates, all wavelengths are allowed. So there's more vacuum energy pushing on the outside of the plates than on the inside. The result? The plates get pushed together by the vacuum itself. This has been measured. The vacuum has pressure. Empty space pushes on things. And it gets weirder. Those fluctuations in the fields can occasionally get strong enough to produce actual particles. For a brief instant, a ripple in the electron field can spike up, creating an electron. But wait, electrons have charge. You can't just create a negative charge out of nothing. That would violate the conservation of charge. So what happens is you create an electron and a positron at the same time. A positron is the antimatter version of an electron. It has the same mass but opposite charge. Together, they have zero total charge. They're allowed to pop into existence together. And then, almost immediately, they collide and annihilate, turning back into energy. The whole process takes an unimaginably short amount of time. But during that time, those particles are real. They exist. They can interact with other fields. They can affect the energy levels of atoms. This happens constantly, everywhere. Right now, in the space between your eyes and this screen, electron-positron pairs are popping in and out of existence. Quarks and antiquarks are flickering into being and vanishing. The vacuum is seething with activity. It's a boiling quantum foam. You can't see it. These particles don't last long enough to be detected directly, but their effects are real. They change the properties of atoms. They contribute to the mass of particles. They shift the energy levels of electrons and atoms by tiny, measurable amounts. Physicists have measured these shifts. They're called the Lamb shift. And the anomalous magnetic moment of the electron and the predictions from quantum field theory match the experiments to an absurd level of precision. More than 10 decimal places. The vacuum is not empty. It's full of invisible, fluctuating fields, constantly creating and destroying virtual particles. And now, let me bring this home. You, your body, your atoms. What are you really? You're not a collection of solid objects. You're not made of little balls stuck together. You're made of fields, quantum fields, vibrating in incredibly complex, stable patterns. Your electrons, the ones orbiting the nuclei in your atoms, they're ripples in the electron field. Your protons and neutrons are made of quarks, which are ripples in the quark fields, held together by gluons, which are ripples in the gluon field. The photons bouncing around inside your body, keeping your molecules together, are ripples in the electromagnetic field. And all of this is happening on top of the boiling, fluctuating vacuum. The fields that make up your body are dancing on top of an ocean of quantum foam, an ocean that's everywhere, always, filled with virtual particles popping in and out of existence. You are not a thing. You are a process, a standing wave, a stable pattern of vibrations in a sea of fields. Think about a whirlpool in a river. The whirlpool has a shape. It has a location. It persists over time. You can point at it and say, there's the whirlpool. But what is it, really? It's not made of any particular water molecules. The water is constantly flowing through it. The whirlpool is a pattern, a structure, a stable configuration of flowing water. That's you. You're a whirlpool in the quantum fields. The fields flow through you. The particles that make up your body are constantly being exchanged with the environment. You breathe in atoms, you breathe out atoms, you eat food, you excrete waste, your cells die and are replaced. But the pattern remains, the structure persists. You are not the particles, you are the pattern. And here's the final, dizzying thought. The fields that make up your body are the same fields that make up everything else. The electron field that's vibrating in your brain right now is the exact same field that's vibrating in the sun, in distant galaxies, in the cosmic microwave background left over from the Big Bang. You are not separate from the universe. You are a temporary, localized vibration in the fundamental fields of reality. When you die, those vibrations will dissipate. The energy will spread out. The pattern will dissolve. But the fields will remain, and they'll form new patterns, new structures, new beings. You are the music, not the instrument. You are a song that the universe is singing to itself. And when the song ends, the universe will sing another. There are no particles. There never were. There is only the field, vibrating, rippling, dancing in an eternal ocean of possibility. And you are one of its most beautiful, most complex, most improbable waves.